Okay. So far today, you've heard Antoine speak about types in general in Lean, and then Filippo gave a talk about how you can define your own types using structure, and in particular, these type classes, which are sort of kind of structures that Lean keeps track of in the background. So Filippo's talk was kind of more focused on how these things work in Lean. But of course, next week you'll be doing things with Mathlib, maybe even contributing to Mathlib or working on projects based off of Mathlib. And for that, you'll be using Mathlib's very extensive system of structures and type classes. So my talk is going to be trying to give you a bit of a sense of how these things work in Lean, in Mathlib specifically. And in particular, in Mathlib, we learned the hard way. We've made a lot of key design decisions that I'll try to kind of walk you through and help you see kind of why we made the decisions that we made. Okay, so to start with, one thing you might have been wondering this whole time. No? Uh-oh. Almost. Yeah, how to finagle this?
Sometimes you just have to leave it alone for a second.
Okay. So one thing you might have been wondering this whole time is, how come I can't just say, F is a field? Like, why? I just want to say F is a field. That's what it says in math textbooks. Why can't I say that? And in theory, you could. You could define a type of fields, and you could prove, theorems about types of fields. But there's a reason we don't do this. Like, it could be made to work, but the reason why we don't do this is because there's this key thing in type theory that came up in Antoine's talk, where in set theory, a thing can be more than one set, and a term or a thing can be an element of lots of different sets. But in type theory, the key thing is everything has a type, and everything has exactly one type. You can't be of multiple types. If you're of type field, then you're not of type ring. You have to make a choice. So this leads to a problem. Like, if we started saying, there are fields and there are rings and there are groups, the question is, what is R? You might say, well, that's obvious. R is a field. I know this. But actually, maybe there's some lemma about ordered fields, and you want to apply that lemma to R. Well, now you've got a problem because R is a field and not an ordered field. So you maybe say, okay, well, fine, I made a mistake. R is an ordered field. But then you want to apply a lemma about linearly ordered fields. You say, oh, my mistake. R is a linearly ordered field. And then, some number theorists come along and say, actually, we've got all these theorems about Archimedean local fields. And so you say, okay, well, my mistake. R is a linearly ordered local Archimedean field or something. You see, the problem is you can never find the right type for R, because there's always an extra property that you might want to slap onto the type. And until you slap on that extra property, then you can't apply the corresponding theorems. So you don't want to choose once and for all the type of R, because then you're excluding everything else. Ideally, you want to be able to kind of, as you find new properties of R, kind of put them on one at a time. So that's why in Mathlib, we make this decision. We don't say there's a type of fields. Instead, we say there's a type of field structures on F. And so this came up in Filippo's talk. So we say F is a type, and we have chosen a field structure on F. So this is the key distinction. We don't say F is a field. We say F is a type with a field structure. And then we make these properties. But there's still one issue with the way this is used, which is that if you treated these field structures as just another argument to the function, then you run into an issue where you would have to specify it every time, right? Imagine you're giving a seminar talk, and you say, okay, we're doing something about LP spaces. Let's start with 1 over P plus 1 over Q equals 1. And immediately someone jumps up and says, hey, you seem to be assuming that these real numbers are a field. What field structure on the real numbers are you using, right? That would be silly. And then you say, I'm using the ordinary field structure on the real number. Then you write the next line, and they jump up again and say, hold up, for this line, what field structure are you using? That would be silly. And that's what Lean would do. Every time you apply a lemma, Lean would say, hold up, I know you used the ordinary field structure on the real numbers last time, but what about this time? It'd be ridiculous. So this is painful. You could do it, but yeah, every single time you apply the lemma, you would have to say, by the way, I'm using real.field, which is the field structure that we constructed on the real numbers. So this is why we have type classes, because this is painful, but it doesn't have to be painful. There's only one field structure on the real numbers that we would ever want to use. So we tell Lean with type classes that that's the field structure we want to use. That's really what type classes are for. Type classes are for situations where there's some sort of structure, but there's a canonical choice for that structure. There's lots of field structures you could put on the real numbers, but there's only one that comes up in practice. So type classes are the way of getting Lean to automatically remember, okay, yes, there's a field structure on the real numbers, but I know which one to use. It's the one that I've always been using. So the proper way to state something like formalized distrib is to say, okay, it's for all types with a field structure, but the square brackets, that means this will get filled in automatically. You don't have to provide it. Lean will search up for it itself. So if you've seen these square brackets all over the place, that just means you're telling Lean, I don't want to tell you this every time. You find it yourself when I ask for it. And if it can't find it, then it'll throw an error and you may have to do something more fancy. But usually it can find it because the system works well. So how do you do these now? If you've been using these lemmas and rewrites, you've never had to tell it the field structure, you can just use the lemma and it is very happy. So really what's going on here is when you do this rewrite, or even when you write these times and minus and plus, Lean sees these symbols and it says, okay, it seems like you are talking about field operations on the real numbers. Let me go back and check and see if you've defined a field structure, and it sees that you have, so it works well. Okay, so this is why we use type classes in Mathlib. And a little bit of looking under the hood to see how this is all working. So Filippo mentioned classes and instances. So let's see some of that in action. So real.field, if we go deep into Mathlib, my computer's slow, but if we go deep into Mathlib, you'll see that this thing is labeled as an instance. Here we go. So this is the proof that the real numbers are a field, and it's labeled as an instance, which just tells Lean, hey, I'm going to define this once, but then remember at any time you need a field structure later on. So instance is the word for defining these sorts of things. So this may come up in your own work next week. You'll be defining some object, and you'll want to say, oh, it's a group, it's a field, it's something, it's a topological space. You'll use instance so that you define it once, and then don't have to keep providing it over and over again. As another example, so this is where the classes come in. How does Lean know in the first place to be keeping track in the background what things are, what field structures there are? That's where class comes in. So this could be structure. You could say structure field extends common ring division ring. But then Lean would just say, okay, there's this thing called a field, but I'm not going to remember field structures. The class tells it, yes, please, when I start specifying field structures via instances, please remember them and keep track of them so that I can use them later. So those are the two key words that make all this work. It's instance and class. And I think we saw these in Filippo's talk. And then the third thing is using the square brackets so that in theorems, so that they can be used without manually respecifying the instance. Okay. So yeah, please interrupt me if there's questions, but this is this is why Mathlib does things this way.
One question: when you do that check field command, there's nothing in the output that actually says it's a class.
Yes.
You have to click through.
So yeah, so what check does, check is just asking Lean, what type is this? So I'm just using this as a way to click on it. Really, Lean says, okay, what is field? Well, field is just a thing that spits in K and spits out a type, namely the type of all field structures. But abstractly, the type of field is a thing that spits out types, takes in types and spits out types. If you want to know actually what it is, you can probably do print, and it'll give you more helpful information. It'll, okay, here, so now it says it's a class, and so check is if you want to know the type, print actually gives you the information about it. Yeah. Yeah, okay.
So difference between structure and class. It's exactly the same, except that when you want to define an instance, it should have been defined a class before.
That's right. Yeah. So basically,
too late.
Yeah. If you maybe it may feel a little silly, like why can't Lean just keep track once I say instance? But for some reason, probably internally, you have to say class first. If you say instance without saying class, it'll say, hold up, you want me to put an instance, treat this as an instance, but field isn't a class.
If you say class and you could have said structure, then you never use it as an instance. It makes no difference.
Yeah, I assume maybe there's performance reasons if you just call everything a class, but who knows?
It's kind of am I right that if you call everything a class, then when you're doing type class inference, it's one more thing for it to check, oh, maybe this is the class that you need.
Yeah. It'll just be doing a lot more under the hood. Yeah.
Like if you made everything a simplemma, that would be a disaster.
Yeah.
You don't say everything is a class unless you actually want it to be.
Yeah. So Mathlib is very carefully curated. We're very careful. We make kind of long, lengthy deliberations about which things should be classes, which things should be instances, and we try to make sure everything runs very smoothly so that you can prove the math that you want to prove. Okay. So in terms of the Mathlib algebraic hierarchy, so it's built out of these classes, and it uses this word extends that we saw in Philippo's talk, and I think I also saw it when we did field. So field, it extends, common ring and division rings. This is basically saying what is a field? It's a thing that is a commutative ring and a division ring, and you can kind of just click through and see all the various parts of this. So what is a common ring? It's a ring called monoid. What is a ring? It's a semi-ring, icon group. And then here's actually this file is great. It's just a big long list of various worse and worse types of rings. So there's rings, semi-rings, non-associative rings, non-unital rings, non-unital, non-associative ring, just keeps going and going, because maybe someone wants this one day. But at the very bottom, you've got this lovely object called a distrib, which you've never learned about in your algebra class. A distrib is a great mathematical object. It's got an addition and a multiplication that have no axioms, so just two arbitrary binary operations that happen to distribute over each other. So no one's going to study this thing. There's no one going to be writing papers classifying like finite distribs of order 16. But they're there, and they're there because Mathlib likes to kind of build these things up very atomically, kind of very basic. This one has the very basic building blocks of ultimately what will become a ring axiom, but you build these things up very atomically and then slowly build them up just in case someone wants this and not that. By building it up atomically and then kind of modularly building them up, it allows you to kind of have very granular flexibility. Yep.
So then why not separate out two separate classes, left distrib and right distrib?
Right there.
Oh, there it is.
So in case you only have a left distrib.
We get two separate definitions and not have class distrib extends left distrib, class right distrib class.
You could. I don't. Maybe people thought that left distrib and right distrib are so niche that it's not really that helpful, but I think you could. I don't see any reason why you couldn't.
I think the whole point, since you want them to be protected, the projection, then you lose a little bit the interest of extending since you're protecting the name of the field.
I see.
Yeah.
It's a bit technical, almost has an answer there.
Yeah.
I think this is the point.
Yeah. Other questions? Yeah.
And I guess in this inheritance hierarchy, if you extend mul twice, you only get the operation once.
I think so. I think this extends is actually kind of fancy because as you saw at the beginning, there was like the field extends division ring and comm ring, and technically division ring and comm ring both have a multiplication on them. But Linus is smart enough to know all those fields have the same name, so I'm not going to make two of them. So extends is very clever. It kind of looks at all the names in the various structures and it takes the union. It doesn't kind of duplicate them. So yeah, it's very helpful. Cool.
That way, if you define a notation for within mul, that it explains what the star means, and then with any type that extends mul, then you get that notation.
That's right. Yeah.
Sorry if I missed that. What's the difference between extend notation and without extend we have brackets in the second thing? I mean, in the first district we have extend mul r. In the left district class, there's no extension, but we use the bracket.
So technically, there's a slight technical difference, which is I think what this means is if you want to prove, like suppose you've made some new fancy object and you want to prove that it's a distrib, then the extends just means it's copying over the field. So what this means is there would be four things you would have to provide: multiplication, addition, and proofs of these two. So if you were proving that your fancy new object was a distrib, you would have to provide four things. Whereas here, if you wanted to prove that your fancy object was a left distrib, you would actually have to first prove that it's got addition and multiplication, and then only then could you even talk about it being a distrib. So it's a slightly different choice. Sometimes you have these things baked in where you can provide them all at once. Sometimes you have to provide them first and then. So there's reasons to make these choices. I'm not sure why they chose it this way. But there's a
point that you're expected in context. Lean should just figure out what the multiplication and addition is in context, and then you have one more thing to prove.
That's right.
As opposed to distrib, where you're not assuming that you can figure out what multiplication addition is.
That's right. That's right. Yeah. Although I think if you had previously proved addition and multiplication, I think it would figure that out. Yeah, and you just need to provide two things. Okay, and actually, one thing you notice is at the very bottom of the hierarchy is really distrib is not the bottom. The bottom of these things like mul and add. So right, and I think we saw these also in Filippo's talk. Like mul is just the type class of a thing with a binary operation that will end up being multiplication. But the key point is these are the classes at the very, very bottom that allow for notation. So whenever Lean sees a times, the way it knows what that means is it searches through its memory of instances of mul, and it says, oh, is there an instance of mul for this object? And if it can find one, then it knows what times means. So if you want in your own stuff to be able to use times and plus and 0 and 1, you have to prove instances of these mul and add and 0 and 1. So that's how Lean knows that it can, like what times means. It doesn't know it automatically. You have to provide it, but you don't have to keep saying each time what the multiplication is. It just sees the times and then searches up for the relevant instance of mul. And the same is also true for like less than or equal to. By default, if you just define some structure and you want to start saying that things are less than or equal to each other, Lean won't know what you're talking about. But if you define an instance of LE, then Lean will know what you're talking about, and you can start writing less than or equal to between your objects. So less than or equal to is just a class that once you prove an instance of it, then you can start using less than or equal to notation. So these very, very bottom of the hierarchy things are great for kind of defining notation on your objects. So in practice, if you define a new object, you might define mul, add 1, 0, and LE, and then you start proving that it's a group and a ring and a field and so on. Okay, so the next thing I want to talk about is kind of a subtle distinction that comes up in terms of the fields in a structure, and the fields in particular in a class. So you've got a structure that maybe it's a class, and it has various kind of things that are part of it, various fields. And some of those fields may have data, and some may be just predicates, true, false. So I'll give a few examples of this. So algebra is an example of one of these structures or classes. You can see the definition here. And this is for kind of like an extension of rings. You know, one ring, like R is an A algebra, right? It's an extension of rings. And this is an example of a class that has data. What that means is that it actually has a few things. It has data and it has predicates. So it has data in the sense that algebra inside of it contains the algebra map. And then it has some predicates that has to satisfy. The algebra map has to satisfy this, and it has to satisfy this. And this distinction between data and kind of predicates is actually quite important in terms of library design, and I'll show some examples of that. This is something I want to kind of really point out. So some other examples, like all of these ones, like add, mul, 0, 1, LE, these all have data, right? Mul inside of it contains the definition of the multiplication.
So
yeah?
What is protected?
Protected is just something for the name. Oops, I don't know where I was. But protected is just, it's a thing for the name where basically algebra map is actually kind of a common name, and you don't want Lean to get confused, or they usually get confused when they write algebra map. So protected just means in order to refer to this algebra map, you actually have to say algebra.algebra map. It's, yeah, it's a way of kind of disambiguating. Yeah, avoiding name clashes. Yeah, so some fields have data, some fields are just predicates. And a lot of the stuff that Filippo was getting to at the end, where you were starting to get errors, these errors come from data inside of these type classes. So that's why Mathlib tries to be very, very careful with how it handles data inside type classes, and it leads to certain design decisions.
What is data?
So by data, I mean something that's not a predicate, right? So this is a predicate. It's either true or false. It's a prop. It's like either the algebra map satisfies this or it doesn't. Whereas this algebra map, this has data. This is actually a function. It had like it's a function that tells you how to turn R's into A's. So it's more than just a true false value. It has meat to it. Has content. So it's yeah, kind of in like when you like basically yeah, when you say algebra, you're not just saying some predicates on RNA. You're actually saying there's also this kind of extra data. Yeah. Okay. So some other examples of how predicates are used. So predicates are used all over the place. Predicates are great. They don't cause the problems that Filippo was talking about. So just some other predicates, if you work in the algebra library that you may see, One is called, oh, so I should say for algebra, even though it's technically for rings, at least for me, most of the time when I work with algebra, it's for fields. So if you're doing anything with field theory in Lean, algebra is the way that it's used, even though it's usually for rings. So if you want to say, let L over K be a field extension, you say K is a field, L is a field, and L is a K algebra. That's how you say that L over K is an extension of fields. One thing that came up as a problem very quickly in Mathlib is how do you talk about like a 3-level extension of fields? How do you say L over K over F is an extension of fields? You can say, L over K is an extension of fields, K over F is an extension of fields. But then, like, how do you go from F to L? You have to go kind of 2 steps. And what if there's like a commutative square of fields? Then there's like 2 ways to go, and it's very messy. The trick that we found in Mathlib, this is before my time, was to introduce this thing called is-scalar tower. So you may see this popping up in the algebra library. Basically, this is a way of saying a certain triangle commutes. So you have your F, your K, and your L, and they form kind of what is F, F, K, L, but there's actually kind of 3 maps: F to K, K to L, and F to L. And is-scalar tower is a predicate that says that that triangle commutes. So the way we handle like lots of fields and rings flying around, especially in the algebra library, is with this is-scalar tower. And this is just a single predicate. It looks kind of funny. It looks like it has these weird dots. You can not worry about that. But it's a single predicate that basically is something weird in terms of dots because it's very low level. It just in terms of various kind of scalar multiplication operations. But this predicate is saying that the triangle commutes. So is-scalar tower is an example of a type class that's a predicate that says that a certain triangle of field extensions commutes. Yeah?
I think we saw one in Alex's talk, the order topology class, which says that the topology coming from there is a space that has a topology in the order the same with their compatible types.
Yes. Yeah, so Heather was giving another example.
Sorry, I turned out to be anticipating something that you're going to get to. Sorry.
Oh, that's fine. No, yeah. Heather was giving another example, which is this order topology class. This is a predicate. So I'll get to it at the very end. But right, so how do you say that X is kind of a topological space with an ordering that are compatible? Well, you say it has a linear order that has data. There's an ordering there. You say it's a topological space that has data. But then order topology is just a predicate that says that these two are compatible with each other. So sometimes for design decision reasons, we kind of break things up this way.
What is the content of the word scalar in is-scalar tower?
It's because it's a very low, where are we? It's because it's a very low level definition. So you could define is-scalar tower for rings. You could say, 3 rings form an is-scalar tower if these algebra maps commute. But people realize that technically in algebra, if K is an F algebra, then there's like a scalar multiplication operation. You can let F act on K. And so you can actually define is-scalar tower in this very general setting where you have 3 things and they all have scalar multiplication actions on each other. So that's where the scalar is coming from. And then is-scalar tower is this very, very general kind of, whoops, where are we? It's this very, let's see. It's this very, very general kind of, I don't even know how to parse this. It's basically saying if you let X act on Y and then let that act on Z, that's the same as X acting on Y acting on Z. But somehow that's equivalent to the algebra maps commuting. So it's kind of silly. Like it's not obvious at all that this is equivalent to the algebra maps commuting, but Mathlib loves this because it's a very low level definition. You can use it in all sorts of cases.
Anytime you have associativity.
It's basically, yes, except this is not quite it looks like associativity. It's basically an associativity for scalar multiplications, but somehow it's equivalent to 3 fields kind of being compatible. Yeah. So, yeah. Other questions? Okay. So one last one that you may see in the algebra library, there's this one called is fraction ring. So rather than there is a way in Mathlib of talking about the field of fractions, but we don't want to do that because then you can only apply the lemma to the field of fractions. And if you wanted to apply the lemma to Q, which is the fraction ring of Z, you couldn't because Q is not the field of fractions. It's another type that happens to be equivalent to the field of fractions, but it's not literally the same. So this is one of the big uses of predicates is to generalize theorems. Rather than just stating a theorem for the field of fractions, you state it for anything that satisfies is fraction ring. So you see this a lot in Mathlib, where maybe there's a way of constructing the algebraic closure. You don't state theorems for the algebraic closure, you state it for any algebraic closure, and that makes the theorem more general. this sometimes comes up in textbooks, but sometimes they just kind of state it kind of more concretely, and you kind of mentally realize that, oh, it can be applied more generally. So is fraction ring, hopefully this one isn't too crazy to read. It's basically, it's some predicate that says that something is a localization of something else. It's a little confusing, but it's just a predicate that says that F is the fraction ring of R under the kind of algebra map between them. Okay. So this is a common kind of design decision that Mathlib makes, where you make these kind of predicates for various relationships between objects so that you can generalize your theorems. And I want to give one example of how this can get kind of excessive. So this is an example in the number theory library. I'll kind of pull it over a bit. So this is people are starting to complain that this is a problem, and we're trying to figure out how to fix this. But like, this is an example of a theorem in number theory, but you can see it's terrible. You got A and B are rings, but actually they're domains and they're integrally closed. And actually there's an algebra, and actually there's a finite algebra, and then you've got an ideal below and two ideals above, and top one's prime and lies at the bottom, and so is the top, so is Q, and then you've got two fields, and they're fraction rings of the two rings, and then they're in some weird is-scalar tower thing, and it's a finite dimensional extension. It's actually Galois. So this starts to get very, very painful. But in theory, this is technically needed because there's a lot of data that goes into some of these theorems. So people are thinking about ways to kind of mitigate this. It's not a problem yet, but at some point you might start getting pages and pages of these type class assumptions, and then it starts to be a problem.
What can you do? There's nothing else you can.
Well,
They should call it as nice.
That's right, nice, right? Yeah. Well, it be a nice scheme where nice actually means a page of type class assumptions. So, I mean, people are working on like, maybe there's ways of just having like shorthand where lean, like if the same pattern appears lots and lots of times, maybe lean can have some way of condensing that, right? In number theory, there's this very famous like AKLB setup, which is just two rings and two fields satisfying certain assumptions. Maybe you can just have some way of lean remembering that. So people are thinking about this.
There's something that extends but doesn't extend at all, just gives another naming for it.
You can have like abbreviations, yeah. So there are ways of working around this, and people are working on better ways of working around this. Yeah.
Like I never liked that there's no such thing as a vector space. It's always a module, and you
Yep.
make an extra assumption that your
Yep.
ring is a field.
Yep.
Yeah.
Just let me say vector space. Vector space over a ring. Over.
It's some reasons to talk about vector spaces. People believe that modules are complicated. Modules is a basic structure.
People know the word vector space.
But they should not.
So you're really, when you teach linear algebra, you should just be teaching about modules, and then later they're surprised that modules can be defined over things that are not fields.
I believe that we should say modules from the very first start,
Yeah.
and the first year should be modules over fields,
Yeah.
which are easier.
Is fraction ring block?
Yep.
In the second line.
Yep.
Shouldn't you define field F, or do you not need that?
Oh, okay. Technical. Well, it's up here. The variable sticks around. So I define F as a field, and then I'm defining a fraction ring of F. So it sticks around.
Can you check if fraction ring needs field? Can you check if fraction ring needs field?
It doesn't. It just needs rings. In fact, so what does it need? It needs a common ring and a common ring. Better in algebra, yeah. So there's like the total ring of fractions. I don't know. It's general. It's something about localizations. Yeah. Mathlib loves generality. So if you think, is this thing generalized already to this thing? The answer is probably yes.
It's maybe a little off topic, but like, can you have global variables or like local variables so that you don't like overload the same letters and stuff? Just like if sometimes we say, okay, within this section we say F.
Yeah, so Lean has things like this where you have a section and then you end your section, and then outside of the section, now there's no longer an R. So in this, so here R is only divided here.
So for example, here you will need to, within the section, you need to say what F is, because it doesn't remember.
No, it remembers everything outside. If you wanted like if you wanted F to not be remembered, then you put this inside a section.
So variable is automatically global.
It's automatically global to within the current section that's in. So it doesn't escape the current section, but it goes into any subsections. Yeah, which I think that seems reasonable to me. Yeah. Cool. Other questions? Yeah.
What about omit? Like when you omit an instance from the theorem?
Yes, that's a way of kind of it's a variable in the scope, but you don't actually want it, so you throw it out. Yeah. There are, yeah, sometimes there are things in variables that are in scope that you don't want them to be, and there are ways of taking them out with omit, yeah. Okay, so getting back to the kind of design decisions. So as I said earlier, kind of there's this subtle distinction between kind of fields that have data and fields that are just predicates. And so one example of this is inhabited versus non-empty. This came up in a discussion on Zulip. So maybe you want to say that something is non-empty, some type is non-empty. One way you could say this is inhabited. Inhabited is a type class that has only one field, and that field is an element of the type. So basically inhabited is a type class that is basically saying it's non-empty, but it keeps in mind a specific element. So it has data. It remembers which element you chose. So it's kind of, when you're carrying around inhabited, you're actually carrying around a specific element. And the problem is this may be non-canonical. It may be kind of annoying to choose a specific element. It also means, it's kind of annoying. It means that if you have two different instances of inhabited and they have different elements in them, then they aren't actually the same. It causes some problems sometimes. So inhabited is a thing you can use, but usually people use non-empty instead. Non-empty is just saying that there is something, there is some element. It's kind of weird with the inductive, but non-empty is just saying there is something that's in alpha, but it doesn't remember which one it is. So this kind of distinction between non-empty and inhabited is an example of this distinction between data and not data. And usually we prefer not data if we can. So usually if we're stating theorems, we say, oh, this thing is actually, like this space is actually non-empty. We don't say inhabited because that requires choosing a specific canonical element to carry around the whole time. There are instances of inhabited in the library. Like for instance, the reals have one, like 0 is the canonical element of the reals. It's the Cauchy sequence of zeros, but people don't use that. Yeah?
Could you also, could they also have written non-empty using an existential quantifier?
Yeah, you totally could. For some reason, they want to do it with an inductive type because it's a little easier. But yeah, you could totally do it with an existence.
That would not remember the.
That's right. It wouldn't remember. Yeah.
So using non-empty would require choice, which we have, right? Whereas inhabited, you're given the element.
Yes, that's right. So there's kind of various like constructive mathematics reasons. Yeah. Yeah.
That was a bit fast. So non-empty is not the complement of the type empty.
No, non-empty is a predicate on types that says that that type is not empty.
So okay, so it's not telling us that this object is not of the type empty.
No, yeah, because yeah. So what is empty? Empty is also a predicate on types. Well, sorry, no. Empty is the empty type. Is empty?
Yeah, that's what I thought. Like meaning no proof. Right.
Yeah. So yeah.
Oh, is empty.
Yeah. So is empty. X means X is empty. Is non-empty. X means X is non-empty. So these are kind of predicates. These are things that are either true or false. Whereas inhabited X means not only that X is non-empty, but you've actually specified a specific element to carry around.
Do we have like non-empty implies is empty?
Yeah. I mean, yeah. These predicates are exactly complementary. Yeah.
That's not a lem issue. Law of excluded middle.
I don't think so, but I don't know. Yeah, you'd have to ask the constructivists.
Well, non-empty.
Yeah. Yes. For instance, inhabited is kind of like 0. Like remember, there's that type class 0 that just remembers you have a specific 0. Like that. The type class 0 carries around an element just like inhabited does. But usually you want to carry around a specific 0. You don't necessarily want to carry around a random element.
Yeah. They need exclude the middle to show that non-empty.
Yeah.
Yeah, is not. Is either not empty or is empty true for any type.
It is true, but yeah, maybe it requires excluded middle.
What is the definition of empty?
That is a good question.
Empty as a type or is empty as a
Is empty as a predicate?
Empty
yes.
means that you can take it, means you have a function that takes elements and sends them to false. So
Okay, so then what in
Non-empty, it's intro by, there is an intro, yeah, you have to provide an
yeah.
I think is empty would always imply not empty, because that's just double negation introduction, which is always okay, even in constructivist math. That the other direction wouldn't be okay.
That sounds right. Yeah. So constructivists really care about this stuff, but if you're doing like just ordinary non-constructive mathematics, then you should use non-empty because it avoids trouble. Yeah. Okay. So what is this trouble that I keep referring to? So this is the kind of the heart of this. So right, there are type classes that have data, there's type classes that don't have data. The type classes that don't have data are fine, they're no problems. But type classes that do have data sometimes cause issue. And this is the issue that Filippo got to at the end of his talk. These are diamonds. So why is there an issue? Basically, if your type class is carrying around data, then, and if Lean is kind of doing these inferences to automatically go from one type class to another, then maybe Lean is in the background producing your type class, but maybe producing it with the same, well, with different data in two different ways. And then you start getting real thorny issues. So the example in Filippo's talk at the very end was that in theory, using the bad definition of metric space, there are two ways, or actually even using the good definition, there are two ways to produce an instance of topological space R cross R. You could get it by directly, okay, it's here. You could get it by directly taking the product of two topological spaces, and that's the topological space. Or you could say, well, R is a metric space. We take the product of metric spaces with the max kind of metric, and then we turn that into a topological space. So here you have two different ways of producing a topological space on R cross R. And those two different ways produce two different bits of data, two different topologies on R cross R. Now they're the same topology, but like that requires proof. It's not obvious by definition to Lean that the topology from this kind of metric space definition, that the topology from the metric space definition exactly matches the topology from the product topology. This is not obvious. So now all of a sudden you've got this instance of topological space that's carrying data, but it's carrying, there's one carrying one type of data, another carrying another type of data, and Lean doesn't know that they're the same, and they're both floating around, and things get very confusing very fast. And you get these errors. So here's the example that Filippo gave. You define your metric space, you put a metric space structure on R, and eventually you run into this problem where like Lean doesn't realize that some function is continuous because there's like two different topologies going on and things are very confusing. Like it's using the metric space topology, but the lemma that you're using is about the product space topology. And you get these very annoying errors because you're like, hold up, like these exactly match, but secretly under the hood, there's a mismatch. And Lean doesn't show you it because you've told Lean not to show you instances, right? You told Lean, hide these instances, don't show them to me, I don't want to see them. But then when things start to mismatch, you don't see them, and Lean gives you very confusing errors. So this is why we hate diamonds, is because they're very annoying errors, especially for beginners. They kind of start playing with Mathlib, and all of a sudden they get these mysterious errors that like A plus B does not equal A plus B, or like you can't prove this. And they're like, why is this not true? And then someone on Zulip is like, oh, actually, there's a diamond here that we need to go around to fixing. So we don't like diamonds. So in Mathlib, we try to be very, very careful with instances that handle data. We try to kind of do it in such a way that we never end up with diamonds. And for the most part, we're successful. So the way we solve this problem is by basically just really enforcing that everything carries around the exact same data. So the definition of metric space in Lean, okay, a metric space is actually a pseudometric space. So what's a pseudometric space? A pseudometric, okay, here we are. A pseudometric space has a bunch of properties. It has, some metric space axioms. But the key thing is that a pseudometric space, inside its definition, okay, has this thing called a uniform space that's just a souped up topological space. So a metric space has the distance axioms, and it also has a topological space structure and a predicate that says that they're equivalent. Okay, so it looks very strange and fancy because it's Mathlib, but for some reason it's carrying around both the metric space structure and the topological structure and an axiom that they're the same, that they're equivalent. Now, why is it doing this? The point is that basically, let's consider our example. We take R cross R, and we put a metric space structure on it. When we define the metric space structure, we have to provide as part of the data what the topology is. And when we do that, we can avoid the diamond immediately just by saying, oh, well, the topology is the product topology, but the metric structure is the metric structure, and then we prove that they're the same right there. So when we put the metric space structure on a product of two metric spaces, we choose the product topology here. And that resolves the diamond issue, because that means that whenever you take the product of two metric spaces, now it's carrying around the product topology, which automatically matches the product topology because it's the same. So this is the way we resolve diamonds. We just make sure that yes, things carry around data, but we make sure they're carrying around the exact same data. Yeah.
And I guess that that theorem X that you were, was just below what you were showing shows that all the other data is in some sense redundant.
That's right. I don't know where it went. It was somewhere else, but yeah.
Oh, there it is, right at the top of the screen now.
Yeah, yeah. How do you prove two metric spaces are the same? You only have to prove they have the same distance function because technically the topology is deducible from the distance function. It's redundant data, but it's important data because it makes sure we avoid these diamonds.
Sorry, the last thing you said, when you have these two potentially conflicting pieces of data, I think my interpretation of what you were showing us was that when you go to metric space, it includes a proof. You're also forced to carry on a proof that the two conflicting things are not in fact conflicting.
Yes, that's right. But you carry around the proof, but the proof doesn't help Lean resolve things. The proof helps you resolve things. What helps Lean resolve things is by making sure that when two things are in conflict that are being carried around, that they are exactly the same.
But they're exactly the same because you're carrying proof of the fact that they're exactly the same.
No. Because so you have like you have the the metric space structure on x cross y, and it's carrying around. I should move this up. It's carrying around the topology, like it's carrying around a topology and a proof that the topology matches the metric. But the topology it's carrying around is the product topology. Like the product topology exactly matches. So you're ensuring that whatever it's carrying around, it matches what the other guy's carrying around.
You could show the definition of the product set.
Oh, yeah. So where's the product of two metric spaces? That's a good point.
Then you would show that there is.
Yeah. So where is this actually defined? Where do we define metric space dot product for me? Yeah. Let's see. Can I
Prod.
prod? Inst. No. Inst prod. No.
Why do you want? I mean,
Check that x times x is a
Oh yeah.
since that r times r is a
yeah. How does it find this? It finds this prod. Okay. Prod dot metric space max. Yeah.
No, it makes sense.
Yeah. Of course, it makes sense in hindsight.
The product metric space, not L2 or L1.
Okay. And okay.
Oh, that's so.
That's not top. That's T0P.
T0 pseudo.
Yeah, that's right. And let's see.
Alex, but perhaps one thing that also goes towards your
Do you want the?
question. Okay.
Well, it's loading.
Now, so one important point together with all these is that this philosophy of forgetful inheritance goes hand in hand with the idea that all instances obtained by inheritance should just be forgetful instances. So the point is that not only the fact that you are putting the topology inside the structure allows you to define an instance of topological space just by deleting all the other data, because you're just projecting. So you're not reconstructing the topological structure so this is why it's called forgetful inheritance. The whole point is you can only define instances that contain data provided they are forgetful instances.
The naive way I would define a metric space is just give you the distance function and the axioms of being a metric. And
but this creates new data.
Because then you can define given a metric, you can define a topology from balls. And now you have a question about whether the topology you got from R cross R matches the one that you got from.
It will certainly match propositional, but not definitionally.
Yeah.
On the other hand, when you have a metric space, you already have the topology built in it. You define the topological structure by throwing away all the other fields, so you never run into any problem.
So okay, I'm having trouble seeing a very clear place, but I think this is where the metric space structure on a product is defined, and basically it's build the metric space structure ordinarily, but then replace. Okay, I don't know what phonology is, but I think that's the same as also replacing the topology. Replace the topology with something that's more sensible. So I think that's sort of what's going on. But I am no expert in this area of Mathlib, but I think it's basically take the metric space structure, but then tweak the topology to make sure it matches definitionally. But don't quote me on that. Okay, yeah.
I'm a little confused about the effectiveness of this strategy. So we're we're adding the definition of topological space into metric space.
Yep.
Thank you. Adding the definition of topological space into metric space to avoid these diamonds, but a metric space is also a measure space, and so why are we not including like a measure space in there as well? And every time we come up with a new space, why don't we just adding all these to the definition of metric space?
I'm actually not sure. Do we get diamonds from the measure space product?
How is the metric space a measure space?
Or I guess you can like construct one, like you
Like the Borel.
Right.
Although I guess,
It's a measurable space.
it's a measurable space.
Oh, measurable.
Oh yeah, sure, yeah.
Wait, there's not a. Oh yeah, maybe I need to read measure theory again. Yeah.
I'd have to think.
But it seems
The
like
question is whether you get the same sort of diamond if you start looking at like measure spaces, like there's a measurable space instance on the product that's coming from the metric space, but there's also
Measurable space means Borel is like a sigma algebra.
oh, it's a predicate.
No,
No,
a
but it's not.
structure. So yeah. So
But you get one from the metric space and one from the product.
So there's a notion of like the Borel sigma.
Yeah.
You cannot hear.
Oh, sorry.
Can we pass the microphone? Or you can project.
I think so. The place where the compatibility is built in is that there's a type class on a thing that might carry both a sigma algebra and a topology, saying that the sigma algebra is the Borel sigma algebra. So measurable space is, a space. It's a space equipped with a sigma algebra.
Where do you see that in the Can you click through to measurable space? I don't see it in the doc. I'm just curious where.
Yeah, so measurable space is, well, measurable space is what you expect it to be.
So, but where do you see that the sigma algebra is compatible with topology?
No, that's a separate type class.
It'd be a predicate, so it'd be a,
Borel space.
Borel space or something.
Borel space.
yeah.
Beautiful.
So yeah, often these types of things are resolved by predicates.
Same as order topology. So
Yeah,
we already
yeah.
saw the order topology.
Yeah.
So that's another way to fix diamonds?
Maybe, depends. Yeah, so I want to give one last example of a diamond. Basically, so the reason why I want to give this example is if you've ever looked up the definition of a group in Mathlib, you'll see that it's terrible, right? Usually a group is, multiplication, identity, a few axioms. Here, a group is, multiplication, identity, how to raise elements to natural numbers, how to invert, how to divide, because that's not so obvious. But of course, it's equal to A times B inverse, how to raise elements to integer powers, some axioms about that. So the definition of a group in Mathlib is terrible. The question is, why did they do this? Don't they know that you can get the natural number power from the multiplication by induction? And the answer is they do know this, and they didn't have that for a while, and then people started running into problems. So the issue is that suppose I ask, you're doing a proof in lean, and for some reason you need an instance of Z being a Z module. And this seems very straightforward. Z is a Z module. The problem is there's two ways Z could be a Z module. First of all, Z could be a Z module because every additive commutative group is a Z module, right? Z modules are just additive commutative groups. So that's one way that you could get Z being a Z module. But the other way you could get Z being a Z module is that R is always an R module for every R. So there's actually two ways that Z could be a Z module. One is R is always an R module, so there's always an instance of modular R. The other is that every additive commutative group is a Z module. So these are two different ways that Z could be a Z module. And the problem is that they produce identical Z module structures, but it requires a proof that they're identical. One is defined via multiplication. So the ring one is defined via multiplication, Rx and R by multiplication, whereas the additive commutative group one is defined via like induction on the group operation. So these two operations are the same, but the proof is actually it's an induction proof. It's not obvious. Lean can't do that automatically. So you're carrying around these two different Z module structures on Z, and you start running into diamonds in your proofs, and you start getting very upset. So how does Mathlib solve this? It's the same way it solves the other one. Basically, it says, okay, what is the problem here? The problem is two bits of data that are the same type of data, but they're being produced in two different ways. So we'll just add that data to the definition and avoid this altogether. So when you're defining a group, now you have to provide what the, I guess, okay, this is for a multiplicative group, not an additive group, but you have to define, I guess I can say for an additive group, you have to define how Z acts on it. And of course, it's going to be definitionally equal to, there's going to be some axiom somewhere. Yeah, here are the axioms. These axioms say it's definitionally equal to the ordinary way that Z acts on it, but this is extra data that avoids the diamond. Okay, and in particular, where is the diamond really avoided? It's avoided in inst adcon group. So when we say that the natural numbers are an additive commutative group, we don't just define the addition and do the usual group proof. We add a couple extra things, if we can find it. Here it is. When we define the integers being an additive commutative group, we also override n small and z small. Usually you don't have to provide these. Lean will just automatically say, oh, you want the usual one, you want the usual one. But for these, we have to override them. We have to say, actually, the way the integers act on the integers is not going to be the usual way. It's going to be by multiplication so that it matches the other thing later on. So this is an example of how we can solve these diamonds. We add the extra data as a field, and then we override it to make it match when we define the object. So Z is an additive commutative group. And the way it acts on itself is by multiplication, because that'll match the other way later on, and we won't run into problems. Yeah?
So does that mean each time you find, you discover a new diamond, you have to draw in some extra definition into the instances?
Possibly. If it's the sort of diamond that gets solved this way, then yeah. So this is one thing people worry about, is the explosion of these extra fields inside. So in fact, people worry about this so much that I'm going to show you one other diamond that hasn't been resolved. I guess first of all, field. Here is print field. Here's all the axioms of a field in Mathlib. So it's got tons and tons of stuff. The one I wanted to point out is Q small. So here there was a diamond with Q being a Q module. So they said, okay, well, it's another diamond. Let's put another thing inside the field structure, and that solves the problem. It starts to get a bit absurd that this is the definition of a field in Mathlib, but it does solve the problem. Yeah.
But a field isn't a Q module if it has positive characteristics. What's going on?
That is a good point. So how is it defined? Well, basically, yeah. So how is it defined? It's defined. Okay, it's defined. Okay, well, yeah. So you need to provide an action of Q that is equal to multiplication. But how do you move from Q to the field? Well, it needs that's also data to avoid a diamond, and it's defined just to be numerator divided by the denominator. Now it's possible the numerator is 0. Yeah, it's going to be some junk value stuff. Yeah. So yeah, that's right. So this is going to be junk when it's not needed, but when it is needed, it avoids a diamond. So one other one. So at some point, someone said, hold on, if I have a additive commutative semigroup, or maybe an additive commutative group, then I can't I can't raise elements to natural numbers, or I can't act by natural numbers, but I can act by positive natural numbers, because there's no identity, so I can't kind of raise an element to the 0th power, but I can raise an element to the 1st, 2nd, 3rd power. Shouldn't there be an action of positive naturals on A? And people said, well, yeah, you're technically right, but the problem of putting this in Mathlib is if you add an action of positive naturals onto A, then you get a diamond, the usual diamond, where if n acts on itself, you get some problem where kind of n acting on itself, there's two different ways n can act on itself. First, because everything acts on itself, and second, because positive naturals act on additive commutative groups, that you immediately get a diamond and everything's problematic. So there was a discussion on Zulip a while back where someone's like, shouldn't we have this? And people are like, yes, we should, but that would mean adding yet another extra field to these, like to the definition of a group. We already have like how natural numbers act on the group, how integers act on the group. Do we really want to add how positive naturals act on the group? So this is not a great long-term solution, but so far it's working until you want positive naturals acting on your space, and then you have to persuade everyone on Zulip that this is a good idea.
Can you show the error message at 252?
Yeah, the error is, yeah, what is the error? It rewrote. And this is a terrible error if for a beginner, because you're like, hold on, you say you can't find A dot B in here? I'll show you A dot B, it's right there, right? So this is horrible for a beginner.
Thomas, can you show us how to debug this? Like, I mean, at least I can remember how I would like stick in the A and then I do a conversion.
Oh yeah.
Yeah. So I think it might be interesting to see Thomas trying to track down the error if he's been faced with that.
Yeah. Okay.
For the first time.
Good point. So So how would I deal with this? I've been telling a lot of you that when I have a rewrite or a simp or something that doesn't work, I usually use have statements just to kind of slow myself down. So I would say, okay, I must not be using this limit in the right way. Let's just say have colon equals small equal. And then, okay, well, why is there an error now? It's because I haven't fit in enough arguments. Small equal requires two things, so I'll plug them in, A, B. And then it'll be, okay, that sure looks like, this really looks like what I want. And I still can't rewrite it. And then I would start hovering over things and I'd be like, so what's going on here?
You want to try rewriting to show that?
Yeah, so let's rewrite with this. Still problem. And now it can't find A dot B and A dot B. And so now I'm really confused. Yeah, so what I would do, maybe there's better ways of finding the instances involved, but I would start hovering over these things and being like, okay, what is that H small bit? Like that A is just the A, that A is just the A, the B's the same.
I have to do a conversion.
Oh, very nice. Okay. Yeah, convert. Oh, so
convert this using one.
Or just convert this.
Yes. Okay. Sure. Yeah. Ooh, very nice. Very nice. Okay. Yeah. So yeah, convert is saying, okay, let's check that these two things are the same. What do we need to check? We need to check that the small from this one is the small from this one. Okay. Now you see the diamond. Yeah. Very nice. Yeah.
Can you explain what convert does?
It's like, yes, you hand it. You say the goal is this, and I hand you this. And then it just tries to match them up. And every time things mismatch, it tells you what mismatch is and you have to prove it. Yeah. Okay. Yeah.
Trying to convert the goal to whatever hypothesis you give it as a parameter. Is that what you said?
So it takes something that roughly matches the goal, and then it matches things up and everything that doesn't match it. So basically it says most things match, but here's something that doesn't match. You've got two different smalls going on, two different ways of positive naturals acting on positive naturals, and they aren't the same. You have to prove that.
So if you go to the previous line, if we didn't have this diamond issue, then convert this, it would match A above B in this to the A above B in the goal, but it wouldn't match the right-hand side. So it would say, I don't know why A star B is equal to B above A.
Yeah, so if I took out this definition here, this bad definition that's not in Mathlib for good reason, and then I did convert this, yeah, so the left side would match, and it would just say, okay, then it would start kind of.
You converted too much. That's why I was saying using one.
Yeah. Oh yeah. Okay. Yeah. So now it has to prove that B dot A equals A times B. Yeah. Yeah. If you did full convert, it would be like, oh, okay, you want to prove that B equals A and dot equals times and A equals B, and that's too much. Yeah. Okay. Yeah. And so the last thing about how Mathlib tiptoes around these issues that we kind of touched on a little earlier is often. I mean, so yeah, Mathlib loves type classes that are just predicates because they completely avoid this issue. So if you can kind of keep the data carrying type classes to themselves and then just slap on predicates, that's a lovely world. So the way we talk about topological groups, you may find it kind of annoying. Initially, it's like, okay, can't I just say that G is a topological group? First, you told me I can't say G is a type topological group. And now you're telling me I have to write these two things first. Well, the reason why is because of these types of design decisions. We say there's data of G being a group. There's data of G being a topological space. Those are kind of separate bits of data. But now on top of that, we're just slapping on things saying they're compatible. And this is a nice type class. It just has a predicate, no diamonds. So this is the kind of the preferred way of doing things in Mathlib. It means it's not exactly what you expect, but yeah. And the same thing with order topology from before. The way you say that kind of X is a topological space and a linear order that they're compatible is you say it that way. There's an ordering, topology, and they're compatible. Yeah.
So why can't you omit the first two square bracketed things if indeed
it'll throw an error? And the reason why it'll throw an error is because of this definition. So topological group, how is it defined? It's defined, so again, this is the difference between putting them as extends versus putting them before the colon. So in order to even say topological group G, G first has to be a topological space and then a group, and then you can ask whether or not it's true that they're compatible. So this is a common design in Mathlib. You'll have the data as kind of hypotheses and then various predicates about how the data relates to each other.
And this is a case where it's not introducing fields that haven't been already named.
Oh yeah, yeah. So it is using extends for for various compatibility. Multiplication is compatible with this, yeah.
But it's maybe worth mentioning here that I recently learned there's a variable question mark command that
Ooh.
will help you. Like if you just write this topological group, will tell you what you need to add before it.
Oh, very nice. Try this. Nice.
Well,
Yeah,
it still
then
keeps the
you
question
can
mark.
just keep the stuff after
Yeah.
the equal to.
Well, that is very cool. Thank you.
after the add.
Try variable question mark is manifold m or something like that. IM, I guess, is with a question mark. I think you need to say IM. It takes two.
You use square brackets or
What? I am? Oh, you sorry.
No, like you need square brackets, but you also, it takes two arguments, not one.
Oh, sure. Okay. I am. Oh, I see. Oh. Oops. The problem is I have an import. This is me being silly, and if you know the file off the top of your head, I can import it. This is me just working in a weird.
control space.
Like, do you know the file? Or?
Geometry.
Manifold.is manifold.basic.
This is me just working in a file that I've been working in. The problem is it may take a second, but yeah.
Or the crazy number theory example you had earlier would also be.
Yeah.
Foo is just a generic, like Ida or Bob. I don't want to give it a name.
It's I infinity m.
What?
We need a number. Let's say I and then 3 and then n.
Oh, a 3 smooth manifold or something? Yeah. Okay. Well, I guess we're at time. Should we wrap it up there, and then whenever this finishes, it'll pop up, and anyone who's interested will see the output when it shows up. Yeah. Oh, yeah?
Can I ask maybe a similar question? Is it using one? Convert this using one?
It's kind of like depth. It's saying only go one step.
Okay.
Yeah.
So kind of like rewriting your nth term. Like
Yeah,
your
it's like-
sort of specifying just
It's refining kind of the capability. Yeah. Oh, here we go. Maybe. Oh. Oh, there's like pre-dependent. You might need to first provide topological space.
Huh? Maybe there's no food.
That shouldn't matter, should it?
That's weird. Okay, I don't know.
Right on.
Maybe some stuff you had written before is interfering. Can you like put it at the top of the file?
Can you use the mic? Sorry, because we don't. All this interesting discussion.
Oh, well, I have a mic. I don't think the stuff at the top in the file is going to be interfering.
Yeah. Okay.
I'm not sure.
I don't know either.
It's probably just a variable question mark failure.
I don't think so. I didn't intend to. Come on, use the mic.
I don't know. Yeah.
I think that is cool. You could do inner product space. Well, actually, none of this is going to work without the right input. So just
Yeah. Okay. So I guess for exercises, assume. Oh, you want to say?
Yeah, I think we're gonna take like a 15-minute break and then come back and talk about next week and,
Oh, yeah.
and talk about some questions. So let's first.
Cool.